Hello, this is Spencer Lyon, and in our lecture today, we are going to continue learning about Julia and dig a little bit more into its type system and what Julia calls methods. In order to follow along, you'll need your laptop or computer ready to go with Julia already installed, which we have already covered in the Julia intro lecture. Our main goals and outcomes for this particular lecture are to understand the building blocks or key components of the Julia type system, which are abstract types, primitive types, composite types, and even parametric types. We'll learn how to define our own custom types so that we can organize our data nicely into structs. We're going to learn about Julia's killer feature, which is called multiple dispatch. And then we'll learn how to leverage multiple dispatch so that we can really customize our behavior across all the types in Julia, whether they're built in or we define them ourselves. Key references are these notes here. The Julia documentation on types and methods, very helpful. And finally, the Quant Econ lectures on types and generic programming are also a great resource. So Julia, as we've talked about previously, is very expressive and pretty easy to write, but it's also very efficient at runtime. We talked about how this happens because of the underlying compiler technology that Julia is built upon. And our main method or approach for interacting or guiding the compiler is by defining custom types and then methods that operate on those types. So the compiler technology is there, and we tap into that power using the type system. The reason we're going to discuss types and multiple dispatch together is because they really do go hand in hand to make Julia a very productive and efficient uh, language to do data work in. So let's talk for a minute about what we mean when we say the word type. So each piece of data in our program, once it's defined and ready to be used, is typically going to reside in our computer's memory or RAM, and whatever machine happens to be running our Julia session. Now, it's convenient for us to assign a name to that data, and in that case, we'd call it a variable. So, for example, if we have the statement x equal the string hello, we'd call x a variable. Now, if we dig under the hood a little bit, a variable has three main components. First, we've got the actual data. These are the zeros and ones that computer scientists call bits that represent the data itself. We don't typically deal with things at this level. The second is an address to where the data actually is physically stored within the RAM or the memory on our computer. So it kind of looks like this when we have a variable. So in our computer, there are a sequence of zeros and ones just laid out in our RAM. And suppose the variable that we are working with is represented by this subsequence of zeros and ones. This would be the data of bits, and then the address is just going to be a marker or a note of where the data begins for the variable of interest. So it would point right to this initial zero within our variable. Now, it's not very convenient for us to remember and work with these memory addresses. So often we will have a symbol that represents this address, and that's the name that we gave it. So we'll always refer to our variable using the name x, but kind of under the hood, we know that x is really some reference to this memory address, and then it also knows how long the memory should be to store our data. So it would get this subsequence for us. Now, in Julia, when we have a type, it represents our the type of or the kind of data. So is this a string? Is this an int 64, etc.? And it tells us the address. Julia is going to use this information in order to enable some syntax and then decide what's possible for us to do with the data. We're going to see a lot more about this, what behaviors are defined on the data today. That's our main goal. So, how does Julia think about structure and organize types? Well, in Julia, types are organized into a hierarchy, almost into a tree based structure. And at the very top of our hierarchy, we have the any type. And this is a parent type for everything. So, whatever piece of data you happen to have, if you ask Julia, hey, is this a type of any? The answer will always be yes. At the very bottom of our hierarchy, we have this what's called the empty union, and it's written union, curly brace, open and close. And the feature about union is nothing is of type empty union. So somewhere in between this top type of any and bottom type of empty union, we have a very rich kind of hierarchy or family of types. And we're going to try to fill in the blanks today of what goes in here. And we'll understand why thinking about this type system as a tree or a hierarchy is going to be really powerful. So, if I were to fill this in a little bit more, you might have types that branch down and look like this. And then eventually they all kind of funnel down into this union type. So, we would have more branches going out. And then each of these kind of branch points would be a name of a different type. And we'll fill this in a little bit as we go ahead. So let's talk about the different flavors or types we might have in the type system. The first one we'll talk about is called an abstract type. Now, these can't be created for us. They are just there to serve as nodes in that tree to help us organize our types into families. And once we talk about multiple dispatch, you'll see really why this is such a powerful concept. The second main flavor or family of types is called a primitive type. And this is typically going to be provided to us by Julia, and it's just the primitive representation of a number of bits. So, for example, a float 64 is a primitive type that represents 64 bits of information to represent a floating point number. A bool is a primitive type with a single bit that is either 0 or 1, representing false for 0 and 1 for true. And then an int 8 is going to be the name of a type representing an integer used that takes up 8 bits. The more we have, the more bits we have, the bigger or more rich the types of numbers or data that could be represented. So that gives us a little bit of flexibility on memory management because if we know we're only working, say, with a discrete variable, maybe we're doing a machine learning task and we have 10 different categories. Well, we don't need 64 bits of memory to represent one of 10 discrete values. We could get away with something like an 8-bit integer, which would take up far less memory and be a bit more efficient for the computer. So Julia is very descriptive about how much memory each of its types takes up, and it lets us choose whatever's appropriate for our application. It's possible for users to create new primitive types, but we usually don't do that. So we'll just leave our discussion of primitive types at Julia provides them to us to organize a collection of bits. Finally, the last main flavor or family of type is called a composite type. And these are kind of what you typically would think about in an object oriented language like Python as a class. So these are types that contain additional fields within them, and we'll create them. We'll create one instance of a composite type, and it has some children or some data members as part of it. Just a note here, if you have a variable, you have a concrete piece of data, it will either be a primitive type or a composite type. There's no way to instantiate or create an instance of an abstract type, and there are no other flavors of type besides primitive and composite. There are some specializations, kind of submembers of this composite type family that we'll talk about, but everything that we create will either be a composite or a primitive type. So let's talk about abstract types for a moment. What do they do? If we can't create them, why do we even have them? Well, abstract types really help us form the structure of that tree. So if I were to draw out a little bit more of that tree, we know that we start with any at the very top, but then underneath any, it tells us we have number, and this is defined right here, where we say abstract type number end. This syntax less than colon says is a subtype of. So underneath number, we have real, and then underneath real, we have abstract float. We also have integer. And the way I got this, so I'll just kind of label these branches here. So this would be branch number 2, branch number 3, and 4. And we see those right over here in the code. So this is 2, 3, and 4. In our little snippet, we also have branches 5 and 6, telling us that as abstract subtypes of integer, we have signed and we have unsigned. So this structure right here that we've been going through is actually the real Julia code for how the number system in Julia is defined. So if we click this link, which we'll do in just a minute, we would see this code is part of the Julia code base. And what this lets us do is it says, okay, I know that if I have an abstract floating point or an integer, I know that these are real numbers. Another type here that we didn't include, there is a complex type to represent complex numbers. Pardon my typo there. We won't talk about this for now. It is there, but we'll focus mostly on real numbers. Furthermore, if we have something that is an integer, not only do we know that it's real, but we know that it is a number. Also, we know that any integer is an instance of the any type. So suppose we have data. Suppose we create a variable x equals int 8, and then we give it the number 4 as the actual value here. So the name of the type is int 8, and kind of underneath this signed, we would have a whole host of int 8, int 16, int 13, or sorry, int 32, etc. So I'll just put int 8 right here, but I'm going to draw a little box around it. This is going to be a primitive type. So we've created our primitive type int 8, and it's true that this variable x, which has type int 8, is an instance of signed, integer, real, number, or any. So if we were to ask Julia, hey, is x an instance of signed? It would say yes. If is x an instance of number? The answer would be yes. If we ask, is x an instance of abstract float? The answer would be no, because we don't come down, we don't reach abstract float as we traverse back up this hierarchy of types. Let's clear our drawings away and carry on. Let's take a quick look at the Julia source code. So here I'm going to click the link and open this in a new tab. And here you'll see we are in base Julia. So this is where the language itself gets defined. And here is that exact snippet of code. So what we just went through is actually how the code is defined in Julia. Notice the syntax. We write abstract type, we give it a name, and then the end keyword. And if we happen to have a parent type, because we're creating kind of a hierarchy here, we'll use the less than colon, which we read in English as is a subtype of. So real is being defined as an abstract type that is a subtype of number. Notice if we go down a little further, we'll start to see these primitive types get defined. So primitive type float16 is an instance of abstract float with 16 bits of precision. We see float 32, 64. Here we start to see some of our integer types being organized. Note that some of these are commented out. If you go to the very top of this file, you'll see it says commented out definitions are implemented in C. So a very small portion of Julia is implemented in C just to kind of get things going, to jumpstart things. But the vast majority of Julia is going to be written in Julia. And we don't need to look at the rest of this yet. We're not quite ready for it. But here's just a sneak peek into the actual type system of Julia and how it gets defined. Okay, back here on our slides, we are ready to move ahead to the next slide here. So we just spent a few minutes talking through the abstract type system. We use the keywords abstract type in order to define one, but if we can't create them, why do we even have them? Well, the main reason, practically speaking, to have these abstract types is that we can now introduce shared functionality that applies to the whole family of abstract types. So, for example, we could define functions on the real type that would apply to any number that's a subtype of real and nothing else. Here's an example. So suppose we wanted to create a function called isInt that just returns true or false if the variable we pass in happens to be an integer type. So without abstract types, if we only had access to these primitive types, here's what this function might look like, how we might define it. So we'll say isInt1 is the name of the function. It takes a single argument x. And then for t, this is just a placeholder for a type name in this array of types. If we have that x is a type, is a t, then we'll return true. Otherwise, we'll finish our if, we'll finish our for loop, and then we have to return false. So is a, or is a, this is a built-in function that takes a variable and the name of a type, and then just tells us true or false if the variable is an instance of that type. So this works. If we looked back at the Julia source code for anything subtype of integer, this would be the list. And we can test this out. So once we've defined this, let's go ahead and let's create a new cell here for us to play around with. And actually, I'll just put it right beneath. So let's go back. And then if we want to try this, we can say is int 1 for 10. And then in a tuple, we'll say is int 1 hello. And this will tell us the first one was true. 10 is an integer and hello is not. Function totally works. It's valid. It's not that much code, probably about 10 lines here. But with abstract types, this gets a lot more simple. So let me show you what the version of this function is if we allow ourselves to use the abstract type. First, we specify a generic version that says, hey, if I'm given a variable x, no matter what it is, I'm going to say that it's not an integer. I'll just say false. I'll have another version. This is called another method of my function. And this time, the variable x, if it is any subtype of integer, I want you to return true. So this double colon is the way that Julia restricts or specifies the type of a variable. And what happens is when we run this code is int for 10, let's try that same example, is int hello. What's going to happen is when Julia is asked to run or call this function, it's going to look at all the different methods or versions of the function and then use the one that is most applicable. So here we're saying is int 10. Julia is going to look at these two different versions of the function and say, all right, I have two options. Either I have the variable is some type of integer or it's something else. For 10, Julia will recognize, hey, this is some type of integer, and it will call this version of the function or this method. In the case of our string, it's not true that hello is a subtype of integer, so it has to use this method or this version of the function. So when we evaluate this, we get that isInt 10 is true and isInt hello is false. So same answer, but quite a bit simpler in terms of the code we had to write. And it's also going to be quite a bit better in terms of the code the compiler has to write. So let's take a look at this. Well, we'll go back to this in just a second. So we're going to talk about this code lowered real quick. So this is going to show us kind of the nitty gritty code, if you will, that Julia is going to use right before it sends it to the compiler. And if we use the isInt function, it says, all right, first I've got to create this vector, or this array of all these primitive types that we laid out in that list. Then we're going to iterate over that. If we're not an integer, then go here. And it's just kind of going to go, we're not going to read through this whole thing, but basically it's showing us that we're going through this loop. And notice this is the kind of code that gets executed for this version of the function where we had the loop and we pass in a string. If we continue on, we can test again the version of that function that has the loop. It has the number 1 at the end. But this time we're passing in some integer. And notice that the code is exactly the same. There's no specialization, there's no optimization really going on here. We just get the same code. On the other hand, if we look at the version of our function where we used the abstract types, if we pass in a string, the only code that gets generated is just to return false. It's very similar when we defined it. All we did when we defined our code was we just said, if I have x that's some arbitrary non-integer type, return false. So not only was it easy for us to specify right here, but the compiler really liked it because now it can just generate a single return false line, and we don't have a lot of this extra code here going on. So that's a little bit about abstract types. And now we'll move on to the second major family of types that we will define and work with in our Julia experience, which is called a composite type. Now, abstract types are really useful and helpful when we want to hook in to what Julia calls multiple dispatch. dispatch. So we just saw an example of multiple dispatch, and what it means is we can define multiple methods of a function or versions of a function, but the code is going to depend on the types of the arguments. So again, multiple dispatch is defining multiple methods for a function with the same name, but the code can be specialized based on the types of the arguments. That's the main purpose for abstract types, but often when we're, say, defining a model or pairing a simulation, we want to create a type that can hold some data. Now, we want to create maybe a hyperparameter type that can hold all the hyperparameters for a machine learning model. And in order to do that, we're not going to rely on abstract types, but instead we'll use something called a composite type. And here's the main syntax for how to create a composite type. We'll use the keyword struct, followed by the name we'd like to give our type. We'll then have less than colon, meaning is a subtype of, and we can put exactly one, or at most one abstract parent type. So a couple key points here. We can have at most one parent type, and the parent type must be an abstract type. It can't be another primitive or composite type. So this is how we set up the name of our composite type and its heritage. And then before the end, we can just list out the different properties or members or fields of this type. So here's how it works. We give each field a name. Here I'm calling it field 1. And then if we want to, we can tell the compiler, we can say, by the way, this field is going to have this particular type. It's possible that we just leave this whole part off. It's totally optional. Same with the parent type specification. And it's also possible to use any type here. We could use an abstract type. We could use a composite or a primitive type. It's totally up to us. In general, it's best to use either a primitive or composite type here, because if we were to put, say, the abstract type integer, that would make our struct a little bit more flexible, but every time we accessed field 1, while our program is running, Julia would have to generate code that checks, well, what type of integer am I? So putting abstract types here is not super compiler friendly, but it is flexible. Maybe we would use that in cases where it's not a performance critical part of our code. Here's an example. I'm going to create a struct called foo. I don't have a parent type. So in our hierarchy, if we were to look at the hierarchy here, we always have any at the top. And then directly below any, we're inserting a new node called foo. And there's nothing in between. There's no abstract types in between. This struct foo is going to have three fields: bar, which can be anything. This leaving off the type is the same as putting any, so this is kind of the implicit default. Then we have an integer field called baz and a float64 field called quux. And to create an instance of my foo struct, I'll just use the name foo, and then in parentheses, I'll pass one argument for each field. So I'll pass the first argument becomes bar, the second one becomes baz, and the third one becomes quux. Once I've created this, I have to define my struct first. Once I've created this, if I ask Julia, hey, what is the type of this little foo object? Well, it is a big foo, because that's what we named our struct. If we try to create an instance or a struct of foo that does not have the right type. So here, a second argument, I'm trying to pass a float, but I told it that we needed an integer. So if I try to run this, it's going to get mad at me and say, wait a minute, I can't make an integer out of 23.5 without some sort of error creeping in. So Julia's going to refuse to even build an instance of foo. with fields that don't have the correct type. One of the methods defined for all type names, so notice this is the name of the struct foo, not an instance of it. We can ask, well, what are the names of the fields? And here it's going to give us back all these fields. And we can then access the fields using a dot. So we can do foo.bar, foo.bads, and foo.quex. If I were to try to do field names of the lowercase, it's going to get mad and say, wait a minute. I don't know how to give you field names of an instance. I operate field names function is only defined on the type. So I either have to say, wait, the type of foo, or just use the type name using the uppercase. So the composite types can also participate in multiple dispatch, meaning we can add extra versions of our functions or extra methods for a composite type. And now what we're going to do is we're going to say is int x, where x happens to be a foo. Well, we're just going to rely on the is int method we already defined on the bar field of our foo instance. So this is going to return true anytime we have a is int foo. Let's put a int here. This is the bar. It has to be an int, and this one has to be a float. So if we do this one, it's going to tell us true. But if I were to put a string here, not an int, and now it's going to return false. So the isInt method is just going to look up the bar field and then check if that's an integer. Notice that this allowed me to specialize the behavior of a function called isInt for my brand new type I created called foo. If we were to check, well, what does the code that's generated look like? We already know what it looks like for a string. What does it look like for a foo? Here it's 2 lines of code. So first line, grab the bar property. Second line, call the other methods of isInt. So this one's pretty handy for us. All right, so this is an exercise that I'm going to encourage you to work through. We're not going to work through it together on this video, but it is a good check to see your understanding. So here's what we want you to do. First, create an abstract type called person. Now that you have this, we want you to create 2 composite subtypes of person. The first composite type is friend, and the second one is foe. Now, for each of these, you're going to be able to have a name field and a height in inches. Make sure you add some types. So whatever you think is an appropriate type for the name field or the height in inches, go ahead and add those as fields on your 2 different structs. And then also, only for the friend type, go ahead and add a third field called favorite color. Again, pick a type for this field so that we're nice to the compiler. Finally, we want you to create a third composite type of person. This one's called stranger, but it doesn't have any fields to it. So we'll just use like struct, stranger is subtype of person, end, with no fields in the middle. So this is kind of going to set things up. It's going to allow you to practice working with the type system. And then part 4, this is going to ask you to work with the multiple dispatch system. So here's what we want to do. Pretend now that using our hierarchy of types, and let's go ahead and draw that out real quick. So what we're going to have is we have any at the top, as always, and then we've created person, which is our abstract type. And now we've got 3 subtypes. We've got friend, we've got foe, and we've got stranger. So using this hierarchy of types, We're trying to see who we want to invite to a dinner party. And our personal rule is that all of our friends are going to be invited. So we're going to create a function called should invite to party. And if we pass a friend as an argument, we should return true. Enemies are going to get a no. So we don't want to invite our foes. Finally, a stranger, if we pass an instance of stranger to should invite to party, it should be a 50-50 toss up. So we're going to have to draw some random numbers and see if it's 50-50. However, we have one caveat. If our spouse says that we should invite a particular person, no matter what type they are, if they're friend, foe, or stranger, the answer is always yes. So we're going to need 4 methods for this function. 3 of them have a single argument, which is the type of person. But this 4th method is how we deal with our spouse's preferences. And it's going to have 2 arguments to that method. You're going to write your code in this cell right here. And then this next one, I'm using the built-in testing framework in Julia to write some tests to make sure that you did your code properly. So here's what it kind of looks like. I'm going to test that you have the right fields on each of these 3 structs. I'm going to create 3 vert instances. So I'm going to create Jim as a friend, Dwight as a foe, and Creed as a stranger. I'm going to check that all of these are actually persons, meaning you set up the subtype properly. I'm going to say we always invite Jim. We never invite Dwight unless our spouse tells us to. And for Creed, it's a toss-up. You never know what you're going to get with Creed. So we're going to just do this 100 times. We're going to send out 100 invites. Half of them should say yes, half of them should say no. So I'm just going to check, is at least one of them true and at least one of them false? Finally, if we're thinking of inviting Creed and our spouse says, yep, we need Creed tonight, then all of them should be true. So this is a quick test case. So what you're going to do is you're first going to write your code in this cell and then execute your code. Then you're going to execute this, which will define my testing function. And finally, you'll uncomment this line, which will cause the test to actually run. So if you've done it correctly, Julia will tell you that all the tests pass. If you've made any mistakes, Julia will tell you which of these tests failed. And then you can go and fix your code. And that's the end of our introduction. So hopefully you take the time to do this exercise and that it's instructive and helpful for you.